First, I want to say that we're really proud to have you guys here for this conference. I know this is your second day, and I want to congratulate Peter Heaney and Steve Shirey for putting on a really great conference. You know, I was standing out in front talking with a few minutes ago with Graham Pearson, Fabrizio Nastola, and Steve. And you know, as Steve just said, I'm a condensed matter physicist. So you're at a condensed matter physics conference. You talk about superconductivity. You talk about quantum materials. Here you talk about the marble floors and how lovely the marble floors are. And in fact, Fabrizio can read the floor we have out in front, and it comes from, I don't remember which mine, but he actually knew where it came from. I think that's really remarkable. Verona. Grazie. So it's really remarkable. So anyway, so I just have a few comments. So for 100 years, the MSA has been encouraging fundamental research into the natural materials that make up our world and, of course, our universe, our solar system, our universe. And your organization has shaped the careers of scientists who have really devoted their whole professional lives to these really interesting problems, understanding the breadth and complexity of materials, minerals. Materials is my business, but minerals, and in the Earth and the planets, of course, in the extraplanetary stuff, and now, of course, with exoplanets, this becomes even more interesting and exciting that there's so many places where you can look for these rocks. Now, I won't go through the discoveries, but I've always been really amazed at mineralogy in the sense that people think of mineralogy as kind of, well, you guys just study rocks, but the amount of discoveries and the influence you've had on other professions, and one which you mentioned, which is my field too, synchrotrons. I mean, it's remarkable the effect that mineralogy has had and the inextricable link between mineralogy and X-rays. Gordon Brown's in the front row here, and when you think about the kind of things that have been developed out of this society, out of the people who belong to this society, it's really remarkable. The history of diffraction, etc. Plate tectonics is another one. I'm just learning a lot about earth sciences and plate tectonics, and you couldn't do it without really being a good mineralogist. And mineralogy itself is sort of the time capsule, if you will, for how the Earth formed over 4.5 billion years, and will also, as I said, be very important for understanding not only your solar system, but the rest of the universe. So it's really a remarkable endeavor, and you guys really have been right at the forefront of that. And the other thing I would say is that you're developing with the world, right? And I'm sure some of the talks today did that, right? There's big data, visualization. These are all becoming more important tools, and I expect that the mineralogy and the kind of science you do will help lead those fields into the future as well. That you guys, when you develop it for your techniques, like X-ray diffraction, when you develop big data and visualization techniques, this will also have an impact on a much broader range of science. So I just want to say a few words about Carnegie. Steve probably mentioned a few things. Like the Mineralogical Society, the Carnegie Institution for Science really has a long, distinguished history. We were established in 1902. This building was, I think, one of our first buildings. Our first lab actually was in Arizona. It was called the Carnegie Botanical Desert Lab, which was to study plants in extreme environments. But our work has really spanned Earth, space, and life sciences, and importantly, the interdisciplinary boundaries between those, which is really, in my mind, what's very exciting and has been for over 100 years. Our mission is to be the nation's, if not the world's, leading independent laboratory. We are independent in the sense that we're not part of a university, and we really have exceptional investigators, as you know, working across these disciplines. The link between Carnegie and the MSA is inextricable, and just a few numbers. I mean, over the past century, 10 Carnegie scientists have served as the president of the Mineralogical Society. 8 have won the Early Career MSA Award, and 9 have been awarded the Ruebling Medal. Most recently, my colleague here, Bob Hazen, he was also a society president. In particular, Bob's work, you may know, extends the studies of carbon deep in the Earth, which very much deeply connected to mineralogy deep in the Earth's surface, and also looking at mineralogy on Mars. So, Bob's work, as well as many of my colleagues here at Carnegie's work, really is emblematic of the way the Carnegie Institution and the MSA have had this extended and deep link for many, many years. So, in conclusion, we're really honored to have you here today. We're delighted you chose the Carnegie Institution, in particular here at P Street, just 6 blocks north of the White House, to celebrate your 100th anniversary, and I want to congratulate you and wish you a great second half of your conference. So thank you all.
Good morning. I'm going to start off the first theme session this morning by introducing this topic, synchrotron-based studies of high-pressure mineral behavior. And I thought I'd just start off by giving a brief intro slide. First of all, introducing our speakers. Dera from the University of Hawaii will be presenting the talk, Putting the Squeeze on Silicate Chains, Unusual Coordination States Accompanying the Densification of Pyroxenes and Amphiboles. And that'll be followed by a presentation by Jin Chang from the University of New Mexico. And her talk is titled Elastic Anisotropy and Phase Transitions in the Earth's Upper Mantle. Both of these talks and their participation in this meeting, and by the way, I really thank the organizers for putting together this great event. Yesterday was fabulous, such great talks. Yesterday evening was wonderful. In any case, the organization Compress is supporting this particular theme this morning. And just to remind you what Compress is all about, Compress is an acronym actually, and it stands for the Consortium for Materials Properties Research in Earth Sciences. And this is a photo of our annual meeting. The last one was held outside of Albuquerque, and you can see the Sandia Mountains in the background, and this is a good representation of our community. The Compress is all about the community. It's a community-based consortium that's funded by the National Science Foundation to enable earth science researchers to conduct the next generation of high-pressure science on world-class equipment and facilities. And in particular, what we are focused primarily on is leveraging the facilities and the opportunities that are present at some of our synchrotron facilities that are run by the DOE. And Compress has beamline scientists and experimental stations on these three synchrotrons: the Advanced Light Source at Lawrence Berkeley National Lab, at the Advanced Photon Source at Argonne National Lab, and the National Synchrotron Source 2, the new synchrotron, at Brookhaven National Lab. And just to wrap it up here really quick, because this is about the talks, not about me giving a presentation, but I just wanted to let you know that what the main types of experiments that we do, although this is not exclusive to Compress, but the things that we use primarily to achieve very high pressures on the synchrotron beamlines are the diamond anvil cell, the DAC, and the multi-anvil press. And here's just a list of the current projects right now that Compress is funding. We have 12 of them. The majority of them are beamlines, basically beamlines that have been in existence for quite a few years, producing what we think is extremely high-quality science. And as an example of that high-quality science, I'd like to hand it over now to the speakers, Przemyslaw and Jin. Thanks a lot.
So I try to call myself mineral physicist or mineralogist sometime, and I'm motivated by the fact that Earth is a very complex and dynamic system. We have these major geologic events that have significant effect on our civilization. We as a civilization also affect the state of the Earth, and it seems logical that understanding the makeup of the Earth, the way it works, is something that we should do to try to live in harmony with the planet. And it seems like understanding how the Earth is made inside, what are the layers, or what kind of chemicals are responsible for the behavior of the Earth is essential. The problem that we are facing as mineral physicists is similar to what was described yesterday for mineralogists who study crustal rocks. We simply don't have direct access to the samples of interest. There have been a couple of engineering projects that try to drill to the Earth mantle, and the record was set in the 1960s during the Kola Peninsula project, when a hole was drilled to the depth of about 11 kilometers, but it's still not enough to really sample the real rocks. We have the ongoing integrated ocean drilling project, which makes some really nice strides. It's trying to drill through the ocean floor because the crust is thinner there. But we also don't have
good samples of the mantle rocks yet from that source. So other than just going with the science fiction ideas of developing vehicles that could take us to the depths, we are left with indirect observations or with experiments that we can perform at synchrotrons with devices that can simulate the conditions of Earth's deep interior. The main sources of information about conditions and properties of constituents of materials of the Earth's interior are indirect, and they come from either analysis of materials accessible on the surface, including excavated mantle rocks from xenoliths or ophiolites, from seismic observations that give us some numerical constraints on what we think the properties and behavior of rocks at different depths are, from studies of meteorites, and from lab experiments that we can perform using high-pressure devices. The problem is that putting together this wealth of indirect information can sometimes lead to wrong conclusions, just like in the case of these blind scientists examining an elephant. I'm a crystallographer, and as you can see in that top corner, crystallography is the foundation of a Mineral Society of America. So I feel pretty good about this. I really like this figure. It demonstrates that you can do these simple experiments, diffraction experiments, that tell you a lot about physical properties and chemical makeup of materials that we walk on and that are buried deep beneath our feet. And this has relevance for mountain range formation and all the big-scale geological processes. As a mineral physicist, I use tools that were developed quite long ago. Diamond anvil cells were invented in late 1950s and mid-1960s here in Washington, D.C. By a group at NIST, or National Bureau of Standards back then, as well as the University of Chicago. Almost right away after the diamond anvil cells were introduced, people started thinking about putting minuscule samples of materials inside, squeezing them, and observing in situ how materials respond to changes in pressure. You can see here a crystal of benzene that was crystallized by Pierre Marigny and Weir. In 1998, I first visited the geophysical lab, Carnegie Institution of Washington, and I met this wonderful group of people. I think some of them are here in the audience, who really pioneered this field of high-pressure crystallography. They measured almost everything that was possible to measure up to pressure of about 10 gigapascals and establish the foundations of what we now call the comparative crystal chemistry in pressure, temperature, and composition space. When I first arrived in Washington, D.C., I was quite naive. I looked at a diagram like this, which is supposed to represent the variety of minerals that dominate the Earth interior. And I thought, does this discipline have future? There's only 20 species of minerals here, and people have been studying them for almost 50 years, so what is left for me? How do I find my own amusement here? And I talked about this with Larry Finger, who was my predoctoral advisor, and he laughed at me and he said, you know, minerals are so wonderfully complex. I've spent all my professional life studying them. I can assure you that there's enough left for you to fill yours. So I'm glad I didn't bet with him, because I would have lost. So I've played with various classes of minerals, and what ended up attracting my attention for longer and more significantly are minerals that dominate these environments that are subduction zones. So these are particularly dynamic environments in the Earth. They occur at the convergent boundaries of tectonic plates, where one of the plates, which is colder, trusts underneath the other one and is subducted into the interior of the Earth, into the mantle. These are particularly interesting and influential environments because there's a lot of earthquakes that occur around the boundaries of these subduction zones. As you could see yesterday in some of the talks, subduction zones have different geometries. Some of them penetrate deep into the mantle, some of them stagnate, either at the transition zone or a little bit deeper. This is a very nice survey that was compiled by Scott King, which shows the distribution of different temperature profiles and tendencies of different slabs that we find around the globe. So the general tendency is that colder slabs seems to have this tendency to stagnate, to flatten at some depth, whereas the hotter slabs, the slabs that are characterized by higher temperatures, do not show this tendency. As a crystallographer, I'm very interested in structural phase changes. They change physical properties of minerals without changing composition. And there has been a talk about influence of phase transitions on the dynamics of the subducting slabs for probably the last 2 decades. One of the effects that has been considered is the effect of Clapeyron slope on the buoyancy of the subducted slab. So if you have a phase transition that changes density in a significant way, and you have a phase boundary between the high and low pressure phases, depending on the sign of the slope, whether it's a negative slope or a positive slope, because the subducted slab is colder than the surrounding mantle, the slope will affect at what depth the transition will take place within the subducted slab. So if we have a negative slope, the transition will be shifted to higher depths and will affect the buoyancy in a way which is shown in this top figure, whereas for a positive slope, it would happen at shallower depths with an opposite effect on the buoyancy. In phase transitions that we find in solids, particularly in minerals, not only pressure and temperature are the controlling factors and composition, but also factors such as compression rate, grain size, strain, and so on. One factor that is quite common and which complicates the picture even more is metastability. So when we have significant phase changes that rearrange the crystal structure to a high degree, an example here is a transformation from diamond to graphite. There is always a activation barrier between these two. So unless a temperature that allows crossing this barrier is reached, phase transitions like this are not observed. And this is what is responsible for being able to enjoy diamonds at ambient conditions, because diamond is not a stable phase. So if we add this effect of metastability, the fact that the subducted slab is colder than the surrounding mantle, we can either enhance or diminish the effect of Clapeyron slope on the depth of phase changes and the buoyancy effect. So if we think about the density changes that happen to minerals as a function of depth, there are some general rules that we have to obey. One of these rules is the dominant coordination state. So Pauling introduced these nice, simple rules that allow us to predict what should be the dominating coordination state for a pair of atoms, a central atom and the ligands. And if we take silicon and oxygen, the 2 atoms that are present in all silicates, we can easily come to the conclusion that at ambient conditions, the dominating coordination environment for silicon, the one that would be preferred, is the tetrahedral coordination. What we find is that as a function of depth, as we go deeper and deeper, the tendency changes. In shallow rocks, we have all silicon coordinated in a tetrahedral arrangement like shown here. But as we pass to the lower mantle, octahedrally coordinated silicon starts becoming the dominant arrangement, which helps to increase density of lower mantle phases. So we have these 2 dominant coordination states of silicon, the tetrahedral one with 4 coordinating oxygens and octahedral one with 6 coordinating oxygens. But if we look through the chemistry literature, there is always a lot of mention of penta-coordinated silicon, which is found in synthetic compounds, but was quite rare in natural minerals. Again, the role that was attributed to this particular structure arrangement is that it would be an intermediate step that could lead us from the lower pressure tetrahedral arrangements to high pressure octahedral arrangements. We know from amorphous substances, from glasses and melts, that pentacoordinated states in which we can assign a coordination number of 5 to silicon are present in these disordered materials that don't have long-range order. But it was thought that for crystalline substances, it's much harder to achieve. As far as I knew, there was just one silicate material, which was studied by Ross Angel and Nancy Ross, in which pentacoordinated state of silicon was described and studied quite extensively. There were also NMR experiments made on this silicate and confirmed that there is a distinct 5 coordinated state. So what I thought is would be an interesting challenge is to take common mantle minerals such as pyroxenes or amphiboles that have very similar structural arrangement and a large variety in terms of types of cations that we can put into the different crystallographic sites, and try to search whether we could use pressure and temperature to induce phase changes that would lead us to these intermediate coordination states. The families of these two types of silicates, pyroxenes and amphiboles, are quite large. Here you see a compositional phase diagram for the pyroxene family. So we have 4 end members of the principal quadrilateral. We have enstatite in the magnesium corner, ferrocylite, hedenbergite, and diopside. As you can see, they differ in optical appearance, but they share the same structural arrangement. We have a family of pyroxenoids, which are very similar to pyroxenes. They have similarly arranged chains of tetrahedrally coordinated silicon, but the symmetry is lower and the corrugation of the chains is much greater. And then amphiboles are closely related brothers and sisters of pyroxenes, in which we have hydrogen atoms, and chains are connected by sharing corner into this arrangement of double chains that you see on the right side over here. So we thought we would survey this system and look for metastable transformation that could happen at lower temperatures, could take place in the subducted slabs, and with hope that we could perhaps find these esoteric 5 coordinated silicon phases. So just to explain a little bit how the structure of this chain silicate looks like and how it's represented, the dominating structural pattern is this chain of corner-sharing silicon tetrahedra. And then we have 2 of these chains on the 2 sides of octahedral slab, which forms this I-beam shape. So the structural arrangement for different species of pyroxene minerals or for different types of phases can be represented by means of I-beam diagrams like this. The silicate chains in pyroxenes can assume many different geometries, many different corrugation geometries. We distinguish 3 model forms, which are shown in the top corner. So we distinguish E chains, O chains, and S chains. And the distinction is based on how the top faces of these tetrahedra are arranged with respect to the top faces of the octahedra underneath. So if the triangle on the top in the tetrahedron points in the same direction as the triangle underneath in the octahedron, this is called an S chain for same. If it points in the opposite direction, it's called an O chain. We think we know the stable equilibrium phase diagram for the pyroxene system quite well. There are 3 dominating phases as a function of pressure and temperature. We have orthopyroxene, orthorhombic phase, clinopyroxene, which comes in 2 different varieties, low pressure clinopyroxene and high pressure clinopyroxene. This, again, is a phase diagram that was extensively studied by Ross and Nancy. And you can see the compositional effect where replacing iron with magnesium shifts the phase boundaries to higher pressures. So we thought that this picture is well established and simple, just 3 different phases. But when we started squeezing these samples to higher pressures, for example, taking the N-statite end member, which has magnesium as the dominant cation. This is work that was done in collaboration with Jin Zhang and Jay Bass, pretty long time ago. We found that these samples at pressures higher than what was previously explored undergo additional phase changes, which change symmetry and affect density a little bit. So we found that orthopyroxene at about 12 gigapascals, depending on the composition, 12 to 14, undergoes a structural phase change which changes the symmetry from orthorhombic to monoclinic, but preserves the topological arrangement of layers. The main mechanism for this phase change is a rotation of tetrahedra and change in the geometry of the corrugated silicate chains. We studied a variety of orthopyroxenes over a range of pressures, and we found that these samples actually undergo a whole series of similar structural phase transitions, which further change the symmetry, further affect the density. And then finally, at around 40 gigapascals, we find something interesting happening. So this is N-statite 90, a sample with 90% magnesium and 10% iron. You can see that there's a phase transformation which changes the coordination where it's marked with a circle from a normal 4-coordinated silicon to a 4+1. So we have an additional bond which is a little bit longer and forms this state that is known from synthetic compounds of pentacoordination. And then at higher pressure, the other symmetry-independent silicon becomes 6-coordinated, so we have a mixture of 5 and 6-coordinated silicon. We looked at the other class of pyroxenes, which are clinopyroxenes with monoclinic symmetry, and diopside was one of the members of this family that we studied first. These are diffraction images collected at different pressures. You can see that there's a point at which there's a very clear rearrangement of the geometry of diffraction peaks. When we solved the structure, we discovered that half of the silicon transforms from the 4-coordinated state into a 6-coordinated state with an average coordination number of 5, but no 5-coordinated silicon present. But then if we squeeze the sample a little bit harder at another 5 GPa higher, we observed formation of 5-coordinated state, again, just by rotation of the tetrahedral chains. Wollastonite, which is a pyroxenoid, which has a different symmetry and slightly different properties than pyroxenes, was another mineral that we explored. There was a reported phase change which was observed by means of Raman spectroscopy. So we thought we would use our single crystal X-ray diffraction method and try to explain how exactly this phase change works. The picture was a little bit more complex because the symmetry is lower and the distortion of the chain is much higher than in pyroxenes. But we found a sequence of 2 phase changes. One of them transforms 4-coordinated silicon, one of the silicons in this low symmetry structure, into a 5-coordinated pentasilicon. This is how it looks in zoom. So we have a simple rotation of a tetrahedron, which brings one of the apices of this coordination polyhedron to a close vicinity of the neighboring silicon, forming a 5-coordinated state. So the solid-state chemists who studied the strange coordination states of silicon linked the presence of 5-coordinated silicon with changes in hybridization of silicon orbitals. So you can see that the different geometries, either the square pyramid or the bipyramid coordinations, they have some interpretation in terms of how electronic orbitals are rearranged at high pressure. So to summarize, we've explored the whole family of pyroxenes as a function of composition. We've explored it to a pressure of about 50 gigapascals at low temperatures, at temperatures that might be relevant to cold subducting slabs. And we found a number of discontinuities, number of structural phase changes which haven't been known before, but might be relevant for explaining the stagnation of subducting slabs. We found that in orthopyroxenes on compression to 50 gigapascals, we observed a complex series of multiple reversible displacive phase transitions. The first one of these transitions happens at pressures which are within the upper mantle depth range, depending on the composition, particularly on the iron content. The first phase change changes the symmetry from orthorhombic to monoclinic, but does not change silicon coordination number. Whereas at higher pressure, phase changes that follow this first one change the coordination number from 4 to 5 and then to 6. In sodium-poor or clinopyroxenes, these phases start with a C2 over C symmetry at ambient conditions. This symmetry is preserved at ambient temperature to pressure of about 40 to 50 gigapascals, above which the structure undergoes a transition involving changing the coordination number of silicon, including 5 coordinated states, like the one that we observed in diopside. And then in chain silicate polymorphs of very calcium-rich pyroxenoids, when compressed at lower temperatures, they also display a series of displacive transitions, which at pressures above 20 gigapascals lead to phases with a mixture of 4 and 5 coordinated silicon. However, none of the observed high-pressure phases with pentacoordinated silicon are quenchable, so they don't really add to the library of phases with pentacoordinated silicon that we could find on the surface. They would only be present at depth. In terms of geophysical implications, there was a group of geophysicists, geodynamists who did simulations of how would preservation of pyroxenes in cold subduction zones affect the buoyancy of the slabs, and they found that the effect is stronger than the effect of preservation of olivine. It could be the controlling factor for whether the slab stagnates or not. So this is pretty much all. So my adventure with mineral physics and looking at crystallography of minerals in diamond anvil cell, I think revealed some of pretty interesting phenomena. I've certainly benefited greatly from being part of Mineral Society of America, as well as member of Compress, which provided the tools that we needed to do these experiments. So I've been having fun with mineral physics and with squeezing minerals. I would like to thank the collaborators. I've worked with a lot of people at various universities. When I was at the Argonne National Lab as a beamline scientist, and I continue some of these collaborations now at the University of Hawaii. You can see here our Hawaiian mineral physics group under a tree. Thank you very much.